Phase shift keying, or PSK, is a digital modulation technique that transmits data by changing the phase of a carrier signal. In this video, we'll see how PSK works and how digital bits are converted into different phase states. Start from the general sinusoidal signal. A sine wave has three adjustable parameters: amplitude, frequency, and phase. Each of these can carry information, leading to different modulation techniques. In PSK, we keep the amplitude and frequency fixed and only change the phase of the carrier signal. Different phase values are then used to represent digital bits, such as 0 and 1. When we shift the phase of the carrier signal, we can create a new symbol. For example, if we allow a phase shift of 180 degrees, we can create two different symbols, one at 0 degrees and one at 180 degrees. These two phase states can then represent digital bits such as 0 and 1. Let's take an example with the bit sequence 0, 1, 0. We start with a sinusoidal carrier signal, and the input message is a stream of binary bits consisting of 0s and 1s. In PSK, each bit is represented by a specific phase state of the carrier signal. When the bit is 0, the carrier phase remains unchanged at 0 degrees. When the bit is 1, the phase is shifted by 180 degrees, creating a distinct signal state. So, for the sequence 0, 1, 0, the carrier phase switches step by step. First 0 degrees for the first bit, then 180 degrees for the second bit, and finally back to 0 degrees for the last bit. In this way, different phase shifts directly represent the digital information, forming the final PSK modulated signal. This is the simplest case, known as BPSK, or binary phase shift keying. In this scheme, each bit is mapped to one of two possible phase states of the carrier signal, typically 0 degrees for bit 0 and 180 degrees for bit 1. This is why, on the phasor diagram, we only see two distinct points located opposite each other on the circle, representing these two phase states. Building on this basic idea, we can increase the data rate by using more phase states. For example, in QPSK, instead of 2 points, we use 4 different phase positions on the constellation or phasor diagram. This allows us to transmit 2 bits per symbol, effectively doubling the data rate compared to BPSK. If we go further to 8 PSK, the signal space is divided into 8 equally spaced phase angles. Each symbol now carries 3 bits, which can be clearly seen as 8 evenly distributed points on the phasor diagram. Finally, in 16 PSK, we extend this concept even more by using 16 phase states. Each symbol represents 4 bits, making the constellation much denser on the diagram. However, as the number of phase states increases, the distance between them becomes smaller, which makes the system more sensitive to noise and detection errors. So, why is PSK important? One of the main reasons is its strong performance in noisy environments. Because information is carried in the phase of the signal, PSK can be more robust compared to amplitude-based modulation techniques. Another key advantage is its efficient use of bandwidth, allowing more data to be transmitted within the same spectrum. For these reasons, PSK is widely used in many wireless communication systems today, from basic digital links to modern mobile and satellite communications. However, PSK also has some limitations. One major drawback is its sensitivity to phase errors, which can be caused by noise or channel distortion. As the number of phase states increases, such as in 8 PSK or 16 PSK, the distance between symbols becomes smaller, making the system more vulnerable to errors. This means higher-order PSK requires a better signal-to-noise ratio to maintain reliable communication. In addition, the receiver design can become more complex because it needs accurate phase synchronization to correctly detect the transmitted symbols. Hope this video helped you understand how PSK modulation works and why it is important in digital communication systems. Thanks for watching. See you in the next video, and don't forget to like and subscribe.